This is a presentation of the paper titled "The Online Search with a Hint" that will appear in the Innovations in Theoretical Computer Science 2021 conference. So let me start with a little motivation that comes from action movies. So let's suppose that you are running the police department of a city riddled with crime, and you know that, or you have some information, you suspect that the terrorists are trying to detonate a bomb somewhere in the city. So you have prepared the bomb squad to act on this information, but of course you do not know where the bomb will be placed. But your squad is placed centrally in the city to be able to cover pretty much the entire area. So one day you get some information and you get a hint that that the bomb is actually hiding to the north side of the city. All right, so you act on this information and you deploy the bomb squad to that particular point. However, it turns out that your hint was given from someone malicious. And this is bad because once you are there, you realize that actually the bomb is hiding on the south side of the city. And now it is too late. The bomb will detonate because you were too far away to act on this information. So this is the type of problems that we are covering in this work. So more precisely, we would like to answer the question, how can we leverage hints when searching for an immobile hider given a search environment? And in particular, in this type of work, we start with an extremely simple environment. So this is the problem of searching on the line. In operations research, this is the problem of linear search. In computer science, we call this the cowpath problem. So there is a hider at some distance from the origin, and you do not know which side of the line it is hiding, and you don't know the distance from the origin. But as a searcher, you would like to be able to locate this hider efficiently, and to this end, you follow a search strategy. And this search strategy in this simple environment consists of going back and forth on the line until the hider is located, and it is completely determined by the lengths of these search segments, if you wish, that I will denote by xi's. Now, the objective here for the searcher is to minimize the so-called competitive ratio of the search strategy, which is a measure of the efficiency of the strategy. It is very simply defined as the worst-case ratio of the distance that the searcher had to traverse in order to locate a hider, divided by the distance of the hider from the origin. And for this very simple problem, we know it has long been known that there is an optimal deterministic strategy that achieves competitive ratio equal to 9, and is based on doubling. So xi is 2 to the I. And of course, there have been many studies of extensions for these problems. This has been a setting that this has been a problem that has been studied in several different settings. And in this particular work, we will consider the setting in which the searcher has some additional information that is given to it. So now the search strategy is a function of this information, which we call hint. And of course, going back to the example I presented earlier, you have to be careful here. So if you knew that the hint would be trusted, that would be great, because you could consider this hint to be guaranteed to be correct, to convey the right type of information you wanted. However, if the hint is untrusted, then you should account for the possibility that it is in fact generated adversarially. So it comes from a malicious source. And we follow the setting in which now the competitiveness of a strategy is determined by two competitive ratios. So the first is the competitive ratio if the hint is correct, and the second, which we call the consistency of the strategy, and the second is the competitive ratio if the hint is adversarial, which we call robustness. And here we follow, of course, this terminology that was introduced that has been used in many recent works on online algorithms with untrusted predictions. There's a nice recent survey by Bitzenmacher and Vasilievsky that summarizes some of the recent work that has been done on this topic. We also follow this framework that we introduced a year ago in ITCS 2020, which we call the Untrusted Advice Framework. But of course, now we applied it to something more specific in the concept of search games. And the reason is that when you look in search games, you can have more specific types of informations and hints that you can use. So here's an example that illustrates what I was just saying. On a line, one possibility of a hint is whether you go to the left or to the right. And of course, a strategy that always trusts the hints is using the previous definitions, 1, infinite competitive. And on the other side, you have a doubling strategy, which simply ignores a hint and is 9, 9 competitive. So which one of these two strategies is better? That's not easy to quantify unless, of course, you rely on the Pareto optimality concept. So now we view these competitive ratios as points on the plane, and what we would like to find is, ideally, we would like to establish to find the Pareto frontier of these strategies, and to be able also to succinctly describe it. And in this work, we consider 3 types of hints. So the first type of hint is the exact position of the target. So here you know exactly where the hider is hiding as a hint. The second is the example I mentioned earlier, the direction of the search, whether you go to the left or to the right of the origin. And the third is a more general setting. Here, the hint can be a k-bit string that conveys a lot of information, as we will see. So before I start, however, let me begin with a property that is quite useful. We know from previous work the exponential search strategy usually are strategies that tend to behave efficiently in these types of problems. So we know, for instance, that if you search on the line using search lengths of b to the I for some fixed b, well, this is what you get as a competitive ratio. And of course, this is a quadratic expression in b. If b equal to, you obtain the minimum, the optimal competitive ratio, which is equal to 9. But since we're studying trade-offs in this model, this expression could be more than 9. So in particular, we're interested, as you see in this graph here, on a quantity that is the largest base for which this strategy can be R competitive. So the largest B for which this strategy could be R robust, in other words. And I will denote this by BR. So this is something that will come up in some of the slides, as you will see later. And this is something to keep in mind. All right. So let me start with the first with the first type of hint. Now the hint is the exact position of the target. So we know where someone is giving us information about where precisely the hider is meant to hide. And in this case, so here's how we come up with a strategy for this problem. So we start with a strategy that is aggressive. So we know that this strategy will be R competitive. So we're using this BR strategy, this exponential strategy based on the lengths BR. But we also shrink this strategy. So we make sure that there will be some I, such that this shrunk strategy. So we divide all search lengths by the same number, basically, to ensure that that we are not wasteful. We reach the target, the hider, without going any further than needed. And it is quite easy to show that this strategy achieves this particular competitiveness. In this context, it takes a little bit more effort to show that this strategy is in fact Pareto optimal. And here you need a helpful lemma. So you need to be able to say that in any robust strategy, the ith length of the ith search segment is not going to be too big in comparison to the I minus 1. So once you have this helpful lemma here, then in fact it follows pretty easily that the previous strategy is in fact Pareto optimal. Okay, so moving on to the second possibility, that the hint is the direction of the target. So now someone is telling us whether the target of the hider is to the left or to the right of the origin. And for this problem, there is actually a related problem that has been studied in the literature, which is the problem of biased search. It was started by Scurer in 2001. So given a search strategy, one here defines the left competitive ratio as the competitive ratio that, assuming that the target is to the left of the origin, and similarly for the right competitive ratio. And the objective here is to minimize the sum of these two. In other words, to minimize the average competitive ratio to the left or to the right, respectively. So we know, for example, that the doubling strategy is such that the average competitive ratio is at most 9, because we know that no matter where we move, we are always non-competitive. So the average is going to be at most 9, or in other words, the sum is at most 18. And Scurer showed that this is tight, that every strategy has a summation of these competitive ratios that is at least 18. And at first sight, you may think that this is in fact this should be simple, right? Because there is no there's symmetry. Why should these two ratios behave in a different way? It turns out that this takes a little effort to show. It's not exactly trivial. Here, Scurer used an extension of Gauss' functional lemma in order to be able to bound the competitive ratios by the supremum of some of sequence of functions, basically. And this is a nice technical approach to it that we will use and extend, as I will show in the next slides. So let's go back to our problem, which is searching with this particular type of hint. Now, of course, we can think of the hint as related to this problem of bias search. So if the hint is to the right, then I can say that the consistency is the right competitive ratio and the robustness is the left competitive ratio, using the terminology of Scurer. And therefore, I know that the consistency and the robustness is at least 18. But the question is how good is this lower bound? And as I will show, we can actually improve substantially on this lower bound. We can get a better trade-off. So let me start first with the upper bound. Okay, so let's assume now that the hint is to the direction to the right of the origin. So what intuitively you could do here is start with any geometric strategy and follow that geometric strategy, but it is biased in the sense that you tend to walk far more towards the direction of the hint than towards the other direction. So to the as we can see here, to the left, I multiply the lengths by a parameter delta that is less than 1. Okay, so this is simple to analyze again. So you can show that the strategies achieve this consistency and this robustness as shown. But what we want to show now is that this previous strategy is in fact Pareto optimal. And right, so what we use here is we use again this extension of Gauss functional lemma, but we use it in a parameterized way, in the sense that that there are some parameters that are hiding in these expressions that are related to for instance to the upper limit of some specific sequence that is related to the length searches of the search strategy. But using this parameterized approach, we can obtain some useful corollaries, apart to the fact, of course, that we show that this is optimal. So the corollaries will illustrate why this lower bound is in fact better than what we get by Scurer's approach. So what we get is that if we want the consistency to approach 5, then R must approach infinity. So as you become more and more consistent, the robustness skyrockets, in fact. And another corollary we get is that the doubling strategy is the unique strategy for which the average of the two competitive ratios is 9. Okay, so I'll move now to the last type of hint that we consider, which is the most general case. Here, the hint comes from a general k-bit string. And let's start first with the case that k equal 1. So if I have 1 bit, I can still convey a lot of information within that bit. For instance, this encapsulates this incorporates the previous setting that we studied, whether we're to the left or to the right, or we could convey information of the form: is the target within a certain distance from the origin? I guess again I can do this with 1 bit. Okay, so So in this case, let's start first with the upper bound. So for the upper bound, I consider these two strategies of the form BR to the I, and the second, so this is a geometric strategy with base BR. And the second strategy is again the geometric strategy with base BR, but I multiply the strategy by a factor, essentially square root of BR with respect to x1. So now the bit decides which strategy to choose among these two, and the bit determines the best of these two. And this is what you follow as advice, as hint. But you can also interpret, in this case, you can also interpret the hint as a partition of the line. So if I denote the two strategies, if I color the two strategies as orange and blue, as you see in this picture here, then if the hint happens to be in the orange partition of the line, I follow the orange strategy, so in this case x1, and if it is in the blue partition, I follow the blue strategy, in this case x2. So these types of problems, the hint has, in fact, a quite natural interpretation. It's not a bit that can be seen to be given out of thin air, if you wish. So what type of results we saw here? So we start first with this upper bound for single bit hints. So we saw an expression for we saw an expression that relates the robustness and the consistency of these types of strategies, and this can be seen perhaps more easy in this figure. So if you want to attain a robustness 9, then you're looking really at consistency that can be as high as around 6.6. Then once the robustness once we are allowed to have bigger robustness, as you expect, that the consistency will go down, and in fact it goes down up to 6.19 roughly when the robustness is 10, and from that point onward you don't get any more gains using this strategy. We also looked, of course, at lower bounds, and we saw two types of lower bounds here. So the first says that any non-robust strategy must have consistency at least 5 with one bit hint. And on the other side, for any robustness, of course, we would like to generalize this. I should say here, okay, I should say here, right. So this the second type of lower bound, we would like to have an expression for any robustness, not just for robustness equal to 9. And indeed, we saw this type of result. Again, you see there is this BR parameter hiding in the lower bound. This lower bound applies to asymptotic strategies. So what are asymptotic strategies? These are strategies for which the worst case robustness is attained for targets that are hiding far from the origin. So you get really the worst case behavior of the strategy if the target is far from the origin. And this is quite natural. We don't really know any strategies that do not have this behavior. We don't know strategies for which the adversary would like to place targets close to the origin. So what this result says is, if you want to get consistency that beats this lower bound, you should start to really think about strategies that are not very intuitive. And we haven't used in the previous work in these types of problems without hints, right? So the proof follows here a typical information theoretic argument from advanced complexity. With one bit hint, we cannot differentiate between two types of robust strategies, and then we need some adversarial argument to claim that neither of them will behave well. So we get the result. And we can generalize the previous result to k-bit hints. The expressions become now more complicated for the upper bounds. We don't really have two good lower bounds here. So the only lower bound we get in this case is that for any robust strategy, we must have consistency at least 3. But I think that this can be improved if one shows some more technical result concerning the lengths xi's for our robust strategy. So we don't need just an upper bound for the xi in comparison to xi minus 1. We need a lower bound for xi in comparison to xi minus 1 concerning our robust strategies, and this seems much tougher to obtain. I will conclude with a lot of open problems that are left from this work and a lot of direction for future work. Of course, we would like first to bridge these gaps between the upper and lower bounds for k-bit hints. And here I'm hopeful that these bounds are tight. I do believe that the upper bounds are likely tight, but we need some better tools, as I said, and as I sketched in the previous slide. Another interesting direction is what happens if we incorporate errors in this prediction. This is the typical framework that comes from the machine learning. Here, the predictions usually come with an error, right? So that would be quite interesting to study. And I should point out here that in some recent work that will appear in AAAI this year with Shahin Kamali, we studied contract scheduling with prediction. So this is a scheduling problem from AI that is very much related to linear search. So we're very hopeful. We're very confident, in fact, that we can incorporate these techniques to answer both types of questions in this context and incorporate errors in linear search. Another direction is to look at randomized strategies. So to study the search games in their full extent, as they were meant to initially. And last, there's no point to study search problems using exclusively the competitive ratio in this context. For instance, if you look at finite search environments, in search theory, people usually appeal to the concept of average search time. And again, you could still apply the same framework. Nothing changes. Instead of competitive ratio, you're looking at the average search time. And you could still look at Pareto efficiency of strategies. So thank you for attending, for watching this presentation. And I should point out here that the full paper is available on archives with all missing proofs.